Okay, we will start the session in a few minutes. Beforehand, we are looking for a note taker. So if someone could volunteer note taking, that would be really great. Anybody interested in taking notes? Some people are interested, please raise your hand. So if someone can take note take, that would be really great. Someone is interested? You got it? Okay, great. Does it work? Okay. And we still need to look for note taker. Wait. Hello, someone want to take a note? We really appreciate your cooperation. It's working? You should look that way. It's not that one, I think, because you should something up there, right? In that case, I can use my.
Use your computer to start, and I'll see if I can get this.
Okay. Just right.
Because that should have displayed. You've got that PGA.
Yeah. Working? Oh. Working?
Do we have any mutators? No.
Not yet.
Good afternoon, everybody. Welcome to Mptcp. Thank you all for coming. We need a note taker or two, preferably. Maybe you can write collaboratively on the Etherpad. We can't start without a volunteer for note taking, please. Christoph, thank you. That's excellent for one. I think we need somebody else because Christoph will be talking for a bit, I suspect. Can somebody assist with Christoph? Oh, thank you. Thank you very much. Okay, that's great. So the blue sheets will start coming round in a second. So I'm Philip Eardley, and Yoshi is the co-chair of this group. It helps if I push the right computer. Just the normal requests here. And the usual note well, which I'm sure you're familiar with now. So here's our agenda for today. We've got a quick update on the status, then some implementation news from Christoph and about the Linux release, and then our normal open mic slot for people who tell us about any other implementation news that they're happy to share. We'll then talk about the protocol BIS document for a while and have some discussion about last calling, which is what we're hoping we can now do. And then we've got a section with 7 nice talks and discussion slots about a variety of topics. So first of all, on the working group status, so there's just some text at the top to remind us of that the primary goal of the working group after we recharted was to create a BIS version of the protocol on the standards track, and after rejigging of the milestones, the most recent update that was due to happen now, the sending it to the ISG. So I guess we're not quite at that stage, but we're hopefully fairly close to it. We talked about, I'm just in the next set of bullets, just some discussion, summarizing just some discussion we had at previous IETFs, that we agreed we needed to have implementation of the BIS, or the revisions that are in the changes that are in the BIS before, in order to push it forward, given it's on the standards track. My belief is, so our belief is that we now have one implementation of everything new that's in the BIS, except for the SHA-256 part. And our belief is also, as far as we know, there is no prospect at the moment of further implementation in the near term, at least on that public Linux implementation, by which I mean it doesn't look like people will have time to implement the SHA-256 stuff in the near term. And our belief is also that all kind of current suggestions have been included in the BIS document. Any changes, etc., have been included, or it's been agreed that they won't be included. So the proposal, this is just sort of to warm you up. The proposal we're going to be making in the discussion session in, I don't know, 20 minutes time or something, is that we working group last call the document now. We send a request to the security ADs to find an early reviewer. And there you go, it's on the standards track. Comments, justifications will be appreciated of that, and all comments, etc. So there are 2 other items on our charter. One is about multipath TCP proxy activity. So the development on that's happened recently is that TCP-M working group has now added a working group item on what's called a converter. So that's good news, and I think that means thereby this topic in our working group has essentially migrated across to there. Of course, it's very encouraged for participants here to therefore get involved in TCP-M and to help with that work. The other topic that we have on our charter at the moment is about an enhanced API, an informational document. So we've got a talk later to discuss about and some enhanced API work that's been done. There's no working group document for this item at the moment, so at some point we'll need to discuss about how we progress with that. So that's kind of the status of where we're at and things. So we'll now move on to the second talk, the second slot, which is about the implementation progress. So, Christoph.
Beforehand, if any have questions, let me know. Does anybody has a comment or question on the chair slide?
Do you want to switch the slides over?
This one. Hello. So just a very short update on the implementations of Mptcp. Next slide. In terms of the Linux Mptcp implementation, we have 2 weeks ago, I think, released the latest Mptcp version 0.94 release. It is released based on the latest Linux kernel v4.14, the one with the long-term support. We are now tracking always the long-term support kernels. That way we can guarantee support for those for a longer time. The main effort in this release was to align it with the upstream kernel. So there were no major new features or changes going in. It was mostly bug fixes and merging it with upstream. But even for a release without any major feature updates, we still had a total of 72 changes coming from 6 different developers of 5 different companies. So there's a community around it with people trying it out, and whenever something doesn't work, they pop up and are trying to fix it. There's also the bigger effort getting more steam in terms of upstreaming it to the official Linux kernel. We have a community that is building up around there with people from different companies, from TSRS, Intel, Oracle, and some others who are also at least in observing this effort. And this effort is getting more steam, and we are trying to design the Linux Mptcp implementation so that we can upstream it more directly. What this might involve that we will probably have to remove quite some features out of the Linux Mptcp v0.94 implementation. But if that gives us a path towards upstreaming, I think that's acceptable. Later on, we can always pull in those features back. So that's for the Linux Mptcp implementation. So we also, Olivier's team at the UCL, they organized an Mptcp hackathon a few weeks ago, and the goal was to leverage multipath TCP on iOS 11 and at the same time deploy corresponding Linux servers. So the goal was to pick iOS applications, find out which connections those applications are doing, which of those connections would actually benefit from Mptcp, from one of those different modes that we are exposing in iOS, and then basically modify those applications, opt them into Mptcp, set up a server, or try to set up a server to use Mptcp for those connections, and then try it out. It was a 3-day event. We had 1 day of tutorial, where Olivier gave a tutorial and I showed the iOS implementations, and then we had 2 days of hacking over the weekend. Go to the next slide. So what happened at the hackathon is the developers, we chose quite a few iOS applications. There was a web browser called Brave, a radio station, some networking measurement tools like NetMeter, and some other custom applications like ProgMP, multipath tester, which Quentin is going to present a bit later today. And in terms of the lessons that we learned is that those applications, they are indeed creating connections that would benefit from Mptcp. For example, the radio station. The radio station it receives a list of possible razor stations, and then it connects to an URL, and the URL just simply starts streaming the traffic, streaming the radio. And for a certain reason that we don't know about, but for a certain reason, this stream, it didn't support to basically easily hand over from one interface to the other. So as soon as we used this application and turned off Wi-Fi, the stream broke. So MPTCP was basically a perfect candidate for this kind of connections. One problem is that the app and the server are often not under control of the same person or the same team. For example, for the radio station, the stream was coming from some third party from the radio station itself. The web browser, he was doing basically search suggestions when you are typing in the search bar. That was a connection that would have benefited from MPTCP as well, because it is a more interactive connection. But even then, the search queries are going to the search providers like Google or Bing, and those are not under the control of the application developer. So that's one problem. And then the other problem is also that lots of applications are using third-party libraries. They're not using the libraries that Apple is exposing that allow to use MPTCP, or they use even higher layer APIs. For example, for radio streaming, they use APIs that are sitting at a very high layer where they cannot choose multi-path TCP support. So there's definitely some work to be done in the third-party libraries, and also for us, Apple, to be done in our own higher layer libraries. You can find some of the projects on the GitHub page that I put on the slides, and you can check them out there.
Any question, comment? Christoph, one question. So about the 0.94 version, so it will be some gap between this version and 0.94. Am I correct?
Sorry?
So I mean, it's not fully implemented everything in this draft, in my understanding.
Yes, it is not the BIS draft. Okay. It is not at all the BIS draft, basically.
I mean, it's based on 6824.
Yes.
Okay.
Absolutely. We haven't published the BIS draft. The BIS draft, we implemented it at the last, in the IETF in Prague, but we didn't publish the code yet at that point.
Okay. Is there any releasing plan?
Sorry?
Is there any releasing plan for BIS draft version?
We should do it. I will figure out the details on my side to do this, to submit my code. The others who participated at the hackathon there should probably also submit their patches.
Thank you.
Thank you.
Thanks, Christoph. So this is now the kind of open mic slot for anybody else who's working on implementations and can share anything about it, what they're working on. We sometimes get somebody who comes and says something, and sometimes we don't. So I'll just give you another few seconds. Okay, right, let's move on. So Alan, I think you're up next.
Hi everyone. Just Hi everyone. Just an update on where we are with revision 10. Next slide, please. Not a lot has changed, although stuff has been added, which makes a change for the last few revisions that were more just corrections. Here we've got two significant changes. We've got the clarification. I don't really want to say it's adding a new feature as such. It's the addition of what happens if you send a fast close on a reset packet, and then also some considerations on TCP fast open. Next slide. So the original fast close option was intended to be a connection level equivalent of a TCP level reset, but for various reliability purposes, and we didn't want to leave various subflows hanging around, we thought that it would be best if that was ACT. However, a lot of the motivation for this is a server that's desperately running out of state and doesn't want to remember anything and just wants to drop on the floor immediately. So this was clarifying what would happen if you put an MP fast close option on a reset. And the general goal is send that on all subflows, which is at any point that a receiver receives a reset with a fast close option, then it can drop all the state and the sender will have dropped the state at the point it sent it all. So it eliminates any concerns around resetting all subflows at the TCP level, when if one of those didn't get there, then the receiver may have retained state. By adding this option to the reset, that means that the receiver knows that this was a connection level reset and it can just drop immediately. So that's all we've done. In draft as proposed by Christoph, it makes a lot of sense, and it was filling a gap that wasn't previously documented. So that's fine. Moving on, we have interactions with TCP Fast Open. So we've got to thank Quentin for writing the original draft, I think, on this. And then was it Quentin? And Gregory. No, several UC Louvain people, thank you for writing this. But we've trimmed down the key points for inclusion in the draft now. The goal of TCP Fast Open is to save one round trip time before being able to send data, and you exchange cookies in TCP options in order to achieve that. So there's two sort of considerations there. How does it interact with Mptcp option space, and when is it appropriate to use it? There is no benefit to Fast Open on additional subflows. Because you already have a subflow, there's no timeliness concern there. Where this is of use is the first subflow, and can we get those HTTP GET requests coming in quicker, for example, which is where it can be used. So if we go on to the next slide, what we've said, we've made the two key observations in this. The first one being the option-based one. So in the SYN, yes, there's definitely enough space. In the SYNAC, it's a little bit tight. The maximum TFO cookie length would only be 7 bytes. But if you're using fewer of your typical options, or you might want to consider which of your fewer options you use, if Fast Open is more important to you, then you could get some longer cookie lengths in there as well. We're just recommending that if servers wish to do this, then they balance how they use their options, because it can be done and it can be useful. The additional observation on this we made is that because a middle box could alter that initial TFO data, but there's no mapping, there's no checksum space in the SYN, you only discover that, or would potentially only discover that one more round trip time further down the line, then you've got no TFO benefit at all if you wait for that option to verify the data. So the alternative solution to this, and the one that we believe to be the right one to recommend, is that the TFO data just stays outside the data level sequence space completely. And it's not until the first non-TFO data starts flowing do we start doing data sequence mapping. That's fine, because there's no additional subflows in use. So there's no concern about getting out of sync in any of that sense. This is just the first initial bit of data is outside the data sequence space until the handshake's completed. It can be delivered immediately to the application.
That only works for the first flow,
Correct.
right? Not for any subflows.
Correct. As we are explicitly only talking on the first subflow for TFO, because we don't see there being any well, for a start, there's not enough option space on the additional subflows, and even if there isn't really any benefit to doing TFO on the later subflows, because the timeliness benefit isn't really there. You've already got the subflow set up, the first subflow. So limiting scope here to purely the first subflow. And that's the changes in the document. That is everything that is outstanding. I believe the chairs now consider this might be worth discussion unless we're ready for working group last call. As far as I'm aware, there's certainly nothing outstanding.
Yeah, still on TFO. I'm not sure
Okay.
if that actually works after all, because what happens if you lose the data and have to retransmit it?
It's no worse than regular TCP in that situation.
But then you still have to examine it from the Mptcp space, right?
You would at that point, yes.
So you have to wait for the retransmission before you can send any Mptcp data.
Do you think that we were talking about this yesterday? That was,
It's attached.
So if the TFO data does not get acknowledged or only partially acknowledged, the remainder part that didn't get acknowledged was basically going to be sent as normal MPTCP data with a DSS mapping, as if after the three-way handshake finished.
I'm not sure how TCP works, because if it gets dropped, you have to retransmit exactly the same data with the same sequence number space.
Yes, the TCP sequence number space will be the same, but at the MPTCP layer, at that point, we are adding the DSS options.
remember, we haven't sent anything with a DSS mapping at that point. So we're in a position we can decide whether that retransmitted data will end up getting mapped or not.
If you add additional information to the packet, no matter what, and the packet was already full size before, then that doesn't work. Like, even if it's just a TCP option.
Well, that's what you're talking about, the option space.
Yeah.
Well, I'm not so sure I follow that.
I'm not sure. I have to look in the details. I'm not sure if there's a problem or not, but I'm not convinced there's no problem. So we should
Okay.
be careful about that. Or are you convinced that there's no problem? Okay. That's good. That's good. Then let me look into it again and try to deconfuse myself.
So another set of eyeballs on this would be greatly appreciated, because when we read the first text, when we put it in the draft, having converted it from the thing, everything made sense. Then when I was actually writing this slide yesterday, I was rereading it going, this is quite hard to follow, and then just discussed with Christoph, and it all became clear. So I admit we're going to need to reword a couple of bits, but if you'd like to double check and send feedback, that would be very much appreciated. Thank you.
Any more discussion about these changes?
Yoshi.
Okay, this is Yoshi from Forum. So I think I have asked this one before, but fast open is a kind of optional thing, so not mandatory to implement.
Yeah.
Yeah.
Yes. Is it purely if you wish to leverage TFO benefits, this is what you need to consider when operating it along with MPTCP? That's what we're saying here.
Right.
That's all.
Yeah, the reason why I asked is, right now we are pushing this draft as a proposed standard. TFO is experimental, so we cannot depend that.
Oh, this is not a dependency. This is a
Right.
documentation of if you wish to mix it, this is what you need to consider.
Right.
That's all.
Right. But as far as I read the draft, it's not very explicit. This is not optional. This is not mandatory stuff. Maybe.
Well, I'm okay. I'm sure we can emphasize that point, that this is a
Okay.
pure if you wish to section.
Right.
It
And
could even
then-
be an appendix.
Okay.
It doesn't have to be in the
Right.
place we put it.
And regarding to that, if there is other part that, you don't have to implement mandatory, maybe we can explicitly specify this is okay, you don't have to implement that. That might be useful, but I don't want to push
No,
this one strongly.
that's obviously stepping slightly off this topic, but it's a good point that there might be some bits of the draft we should,
Yeah.
some functions we could list as musts and shoulds, but that's a very different topic to this, and
Right,
that could
that's
come
a
out
very
of
different.
last school.
Yeah, if we implement, have some opinion on this, I really appreciate.
Yeah.
Because I'm not implementer, so I'm not sure if this is useful or not useful very much.
Yeah, I At the moment, the way it is all written is that all the messages and everything are required for a full implementation, because after all, you as another implementation would want to assume that if you sent, for example, a fast close, it would be accepted. You know, that's why we do standards. It could be worth looking at, but I'm not too optimistic. There's very much that isn't already should and must separated here. So.
Hi, my name is Uma from Huawei. I have no questions on the updates actually, but I have a general clarification question if I may ask.
Okay.
Okay. So in section 2.7, notable features, third bullet says, to meet the threats of identified in RFC 6181, the following steps have been taken care. Keys are sent in the clear in MP capable message, and those are used in basically for the MP join message for hitchmaking, right? So I would like to expand this a little bit. Which threats have been addressed with this on RFC 6181? That'll be great. There are a couple of threats laid out in RFC 6181, including hijacking attacks and a couple of other things.
It's pretty much all those attacks from 6181 about hijacking subflows. The original Mptcp design, and the one we're carrying forward obviously into the BIS because this is only refinement, is that we are always aiming to be no worse. As long as we're no worse than TCP, and sometimes we can be better, then that's our goal. So we have the idea of yes, the keys are in the clear at the start, but then that's the same as if you had intercepted any TCP connection, then you could do sequence number guessing, you could do any kind of thing.
Yes.
When you move into the subflows, those are the threats we talk about in 6181, were about how do you stop someone intercepting a connection, and that's where the keys come in. So those are the kind of threats we're talking about.
If you can expand that section, which section of 6181 is being addressed, that'll be great.
Okay, that's
Thanks.
useful, thank you.
Yeah, thank you. So I think we've heard a couple of useful bits of clarification that need to be done or checking. So that's very good. So assuming there are no more questions on these particular changes, we're now moving on to basically having a slot for discussing whether people are happy for this to be working group last called now. So as we said, that's our in the kind of the default is that will happen immediately. This meeting ends. So just as a reminder, this is on the standards track. We've made some changes compared to the BIS that mean it's the version number has been bumped. So if it will obsolete 6824. So this is your chance. If anybody's unhappy or has concerns about last calling, now's your chance. Otherwise, we will assume that we are happy, and that's what we'll do pretty immediately. Because I think, I mean, you know, perhaps we're not actually expanding on that. We've now had a lot of implementation deployment experience of multipath TCP. We've had a lot of, you know, a lot of interest. It's been used very widely. We've had a lot of discussion about the changes that should be made to that document, and that are now reflected in the BIS implementation of those bits of the BIS. So we've kind of, as chairs, we feel it's ready, but it's a working group decision about that. Yeah.
Yeah, Olivier Balantin. I have one comment about the RFC 6824 BIS, which is the part that describes the experimental Mptcp option, the support for additional options.
You mean the bit that you wrote, yes?
Yeah, I'm the culprit for that. And Quentin tried to implement it, and there are still some issues from an implementation viewpoint. And since this is designed to be an extensible part of Mptcp, my suggestion would be to try to remove that from the core text, looking at the discussion with Yoshifumi before on which part is mandatory and which part is not, and try to write maybe an experimental RFC that describes this additional possibility of having experimental Mptcp option, which is outside the main document.
That would seem absolutely fine. And we can
just as a safeguard to avoid having in the proposed standard spec something which has not yet been implemented.
Yeah, that sounds good. And we can.
Okay.
we can obviously make it clear in the draft about what, there may be additional options sent under this version number, for example.
Yes, so maybe we can reserve one number for the experimental options.
I think actually, I don't think there'd be a problem with that. There's precedent for similar things in other drafts that you have one reserved. You can't have one reserved for experimental stuff, and just go no further.
Yeah.
You don't need to go any further in the proposed standard, and then, as you say, you can write that in a separate doc. Sounds good.
That's the only concern I have.
Any more comments? Okay, so that's great, and we'll expect there's at least 3 comments that have been made here, which will be relevant for that last call. So please make them in writing, and then they'll be taken account of. Excellent. Okay.
Okay. Thank you.
Cheers. So next up, we've got 2 talks and discussions about API issues. So first up is Fabian.
Hello. So I'm going to give a quick update on the Socket API written by Benjamin and Olivier, and I just did a small update for segment routing. So next slide, please. So there is only small change, which is I added the support for segment routing v6, so Mptcp can leverage it. Next slide, please. So basically, what is segment routing? This is source routing. So it allows you to steer packets at the IPv6 level, at the IP level. To do that, the IPv6 data plane relies on something called the SRH, which is the segment routing header. And we think that Mptcp could leverage this to establish the flow that are specific to a path. Sorry, Christophe. Next slide, please. So this is the SRH I was talking about. So this is a segment routing header. This header is inserted just after the IPv6 header. And what's important inside is you have a segment list. So with this, you can specify a list of segments. So for instance, a list of middle boxes where the traffic is supposed to go. So you could insert this on multipath TCP subflow to decide where the subflows are going. Next slide, please. So this is a quick example of the code ported to the API. In this one, I add one of the segments. It's the 22221 segment. So if you do that, your subflow will go through this IP address. So this could open some ideas about what we can do. Next slide, please. So for the use cases, we have disjoint path. So this is one of the idea. You could establish several subflow on several disjoint paths. For the moment, you don't know really if the paths are disjoint or not. Even if you have a 3G or a Wi-Fi or several Wi-Fi, you don't know how close or distant the paths are. With this, you can make it happen. You have several SRH, and when you establish a subflow, you'll know for a fact that they will go through different or same path. It's not the case for the moment. For the moment, we just assume we probe the subflow, we try to understand if it works well or not, and then we use it. Here, you could make assumption, like when you have a retransmission, you could decide to retransmit it on a path that's clearly different from the initial one. So it was discussed in Panergy too about stateless core. If you want a stateless core, you can make multipath TCP work with SRv6 and Mptcp. You can make it work in a stateless core. So we think there are things to do with that. We are experimenting to see what's possible to do. So we updated the API and modified the code to make it possible. So you can just establish several subflow with their own SRH. So several subflow that you'll know that they go through a different path. If you want to test it, feel free to contact me. And if you have ideas about use case or things we could do with that, just tell me. And that's it.
Hi, my name is Uma from Huawei. So how do you get the network path to the host? Which use case you are thinking where you get the network path
Yep. I mean,
known to the host?
there's several papers about segment routing v6 that describe use case. I mean,
Okay.
you could ask a controller to give you a specific path respecting certain condition, like I want this to go there. So for the moment, the application is just an API, right? So the
Okay.
API it just allows you to say, oh, I want to establish a subflow that will go by this path and another subflow that will go via this path. So
Yeah.
that's a bit out of the scope for the API. Still interesting for Mptcp, so
Yeah.
I'm up to discuss
So
it.
I was interesting how a host can know the network path, traffic engineered path.
You can ask
Because
the
that's mostly for, that
you-
is the edge routers, right?
But that's the question. This question is more about source routing, right? It's how do handlers knows where it's supposed to go. You could use a controller, for instance, where you ask him, "Oh, I want this kind of specification for my path. Please give me a path in the network that will respect that." And then the controller sends you an SRH, and you, as an application, you just set the SRH on the subflow. You don't really try. I mean, you can, if you have a smart application, you could try to figure that by yourself. But I think it's the different problem. It's not really related to MPTCP. What's interesting for MPTCP is for path management or scheduling of things like that. No, you know for a fact that those subflow are different or not. So that's what we should focus here.
Well, I got the scope of it, but
Yeah.
I'm just worried about, like, if you're exposing the network paths, which
Yeah.
is designed for operator given to the host, it's open up attacks actually.
Yeah, I mean, yeah.
Srigundavelli, Cisco. Along the same lines, I think, I'm trying to understand, I'm not objecting to this, but I'm trying to understand the motivation for this, right? So in MPTCP, when you bind to a particular subflow, particular IP address, that itself is indicating a specific path. I use let's say I have the UE as endpoint as two interfaces, Wi-Fi and LTE. If I bind to a Wi-Fi address, that is a path all the way to the server, right? So I bind to LTE, that's another path. So in what situations would you indicate a SRH list, or the SID insert SRH into the packet?
Because it's not because you have two interfaces or two different. I mean, you have you have a Wi-Fi and a 3G.
Yeah.
So those are two addresses, two different paths. Yeah, but how different are the paths? For instance, we had that in Belgium, where Proximus provides EDSL, so the Wi-Fi, and also the 3G. If you look at the path, they are not so different. I mean, they could really well. The access network is a bit different, but you end up pretty fast on the same router. So those paths are not really so disjoint. They are close to each other. So the congestion is inside the network. I mean, after when the paths are joined, you don't know that. I mean, at the transport layer, for the moment, you have no idea about what's under. You just see, oh, two different interfaces, two paths. So let's say you have 3 or 4 addresses. And you have to do a reinjection because one of the segment has been lost. You need to reinject it. You have to choose the interface to reinject it. For the moment, what we are doing in the scheduler is just trying to take the best one, but you don't really know if one path would be a better fit to do it or not. Yeah, you could say it's a backup of something like this. Here you have more insight inside the transport protocol to know, oh, this path is probably best because it's totally disjoint from the 2 other ones. That's the main idea. Is you get more insight at the transport layer. Yeah, it's a cross-layer violation, but you have more insight about, I would like to use this path because it's more disjoint, or the opposite is really close to the other one.
Yeah, I think insertion is fine. I think the question is an endpoint, like a host doing that is not completely getting the picture, but how it can, typically it's a default route, right? I use an IP address like Wi-Fi address. It's a default route for me. I never know the path. Unless if you say it's a router, maybe I can understand, but if it's a host doing it, I'm not.
Yeah, it's
I'm
a
not sure.
routing rhetoric in this case.
Yeah. So another question is, like, I think now that, you're opening up this, right? What is the implication to the proxy work that Med and Olivier are doing? Like, will I be able to say that, steer it through the same particular node and there I activate a SID or something, then that becomes my proxy? Will I be able to do that? I'm just curious.
Yeah, I need to think about the interaction with the proxy because we just started with this work and that's exactly what I'm presenting it today. We are trying to see if it's a good idea and what we could do with it.
I think we may be building an alternative solution to that if you go that route.
Okay.
So thanks.
Olivier?
Just one additional comment is that there was a presentation from Daniel Boyer from Bell Canada on Panergy on Tuesday, showing that he wanted to have visibility. He wanted to use IPv6 segment routing inside his core network, and he wanted to expose information about the network to the DNOs so that DNOs can make informed decision. And in the presentation, he refers one of our papers that will be presented next week at Saucer that shows how to expose the information by using the DNS. And this could be a way to couple MPTCP with that information. I will send a link to the paper on the list.
Thank you.
Thanks, Fabian. So next up is Samar.
Hello. Sorry. Good afternoon, everyone. So, firstly, this is my first IETF, so I'm a little overwhelmed with all these guys around, whom I've been always looking at. All right. So, can we just skip to the next slide? This is also about the socket API, which already Fabian has spoken about, and the first thing is I'll talk about the small motivation. Maybe we can go to the next. Yeah. Oh, okay, sure. Thank you. So we were like experimenting with drones, and we realized that what was happening is a drone is flying, and your control signal is not reaching to it because of some reasons. It was just going. You say turn, but it doesn't turn. It collides with the wall in front of it. So we realized that, okay, something is not right. Maybe the link is getting too much congested, or maybe something else is happening. So the idea of using multipath TCP emerged in our mind, and we thought, okay, let's send the control signal on a different path altogether than your standard user data goes in. So that's the basic motivation of this entire work. Okay, so obviously you want your control signals to reach properly, uninterrupted, without any delay, and at the highest priority. So it should be given a dedicated path, even if you have two interfaces. But by multipath TCP in itself doesn't do that, because it balances your data between the two interfaces. Okay, so we thought, let's do something. Let us prioritize one of the path for control data, and to say other path will prioritize only for the user data. But in the event, if a path fails, you automatically fall back to the other path. That's the basic property of multipath TCP. And we were running it over a robot operating system. So I'm not very sure, but everybody's aware of that. But ROS is like, it's a system which gives you an interface where you can control your robots or drones or underlying devices. Yeah. So I think that we can skip. While we were trying to do that, we wanted to have this control sitting at the application layer so that you can prioritize these paths using your ROS interfaces, not directly doing it in the kernel, tweaking it around or doing something. So we came across a couple of socket APIs which were already existing. One was Mptcp info, which was introduced in 0.92. Well, when we started working, it was not there in 9.1. But anyway, the problem here, what we realized is the subflow information was not getting available at the application layer for me to play with. The another was the Hasman's draft, which Fabian just presented. So that's the one which suited to our requirement, at least from the subflow ID being available. So we took up the idea of that from there. And then we built our socket API at the top of it. So can we move to the next one? So what we did is we build a socket API to control the priority of these paths. One of the paths we make as a say primary path using the low prior flag simply, and that is for the control data which is being exposed by your ROS. And for the user data, which is the other link, we make the other path as the primary path. But what we realize here, so when your system is flying or one of the subflow goes down or disconnected because of any particular reasons, and when it comes back, it loses its priority. It doesn't know what priority you have set up a priori. So that was the biggest problem we faced. So there was another modification which we proposed. That's the next one. Can we move to the next slide? Okay. So what we suggest here is, can we have two paths, data structure being maintained inside the Mptcp kernel, which maintains the list of your subflows, which you have set up as a primary path, or the primary path for a particular session, and the backup path for that particular session. So if your subflow even goes down, no issues. Whenever it is being restored, it automatically reads this list from your kernel and sets up the priority flag accordingly. And these are some of the results which we obtained. Yeah, next. So we have submitted this patch to the community. If they are really interested, they can give a look to it. The drones which we had, they didn't support us for us to modify the kernel, so we tested it with the RPi boards. So that's where we stand. Yeah.
Any questions or comments? So Samir, what's the status of your project?
Sorry.
What's the status of your project? Is it a test system or
okay,
a pre-product or?
Yeah, it's still a test system. It is still in the laboratories. Okay, so we have not really deployed it on a drone yet. The reason being, as I said, the commercial drones are really not exposed their kernel to tweak it around. But we have tried it on the RPi boards and placed it over the drone and tested with that. So we are working with some vendors if they can really give us that flexibility. So that's where it stands. Yeah.
So this is Yoshi from Flora. So I have one question. So yeah, I understand your motivation, but so when you establish one subflow and then it's for some reason the subflow is down and then you want to reconnect, but in this case, can we get same 4 tuples before the same previous one? So you might your IP address might be changed or source address might be changed. And then in that case, how we can determine if we can apply same priority or not.
Okay. So here, I have a basic assumption that your source and the destination IP hasn't changed because that list which I have maintained is on the basis of that source and the IP destinations. So I'm assuming between one source and one IP destination, there is one specific flow. So if you're establishing multiple subflows with that, yes, there is a conflict. So all the subflows which will be established between the same source and same destination will come up with the same priority.
And same port as well?
Yeah, a port is not there in the list active that list which we have maintained.
Okay. Any more? Oh, thank you very much. It's very interesting to hear the how it's being used. Okay, next up is Xavier. So, yeah, this is about how to use multipath TCP in 5G. You found the right presentation. So, so very hot topic, I guess, 5G, isn't it? So this is interesting stuff.
Thank you. So good afternoon. So this is a presentation on Mptcp operation in 5G. And I'm presenting on behalf of the co-authors listed here and additional ones listed, as contributors in the draft. Next, please. Thank you. So what changed since the last IETF? A draft was presented in IETF 100 and attendees showed some interest on the topic and pointed to related work from this group and also from research. Especially handling of multiple IP addresses per network interfaces by itself was not seen as a problem because it's common with IPv6. And so we concluded we needed to clarify the problem. So for example, those multiple IP addresses are in 5G provided by different anchors. So what does that mean? So we wanted to explore that. So in this new draft presented today, we take a step back and try to do a broader analysis of what needs to be done. So especially, we take a look at new behavior in 5G that can impact MPTCP. So for that, we found the session and service continuity feature could introduce some changes that are related to MPTCP. And also, another part of the draft described how MPTCP could complement 5G. So basically, that's the dual connectivity feature. Possible outcomes that we envision for this work, that could be a set of guidelines for implementing MPTCP over 5G, a 5G stack, and also possibly derive some requirements for MPTCP for 5G. And of course, we need to analyze them to see if anything there is new or if everything can be done with the current state of MPTCP and 5G. Yeah, thank you. So we start with session and service continuity. SSC addresses various continuity requirements of applications. So it is based on a distributed mobility system. And it has multiple modes. So the mode 1 is fixed anchor. We'll go through the details in the next slide, right? 2 is distributed anchors plus break before make. And mode 3 is distributed anchors plus make before break. So a 5G device selects an appropriate SSC mode for every application, and it is based on the local policy. So otherwise, the network could also set it. So before really going forward with the analysis, I just wanted to speak a little bit about the PDU session, because that's an important topic to make the link between the 5G and MPTCP worlds. So the PDU session in 5G, that's a unit of network service. It can hold multiple QoS flows. It is connected to a single data network and through one or more anchors. And it is associated with a single non-modifiable session continuity mode, and also a single non-modifiable network slice and type. And we'll focus on the IP types, basically. It goes over a single radio access type at any given time, and it will correspond to a network interface on the device. That's what we think to be very probably the case. It will be an implementation choice for the 5G stack developers, but that's the one that makes sense to us based on previous versions of releases. Different applications running on the device may use different PDU sessions, right? So because different applications will have different need in terms of data network, SSC mode, or slice to use. So now on MPTCP, we think that MPTCP should be aware of the SSC mode, because as we will see later, the behavior in this mode can be quite different. And also MPTCP should know the mapping between applications and ultimately network interfaces, because when a new network interface goes up, it may be usable only by a subset of the applications running on the device. So let's, in SSC mode 1, 5G behaves like this. Fixed network anchor provides a fixed IP address to the device. And the network may additionally add or remove additional network anchors, so additional IP addresses, dynamically on the same network interface. And so in this mode, MPTCP should always keep using the initial IP address, because they're the only one which is guaranteed to be available over time in this mode. But when new IP addresses are made available to the application, it makes sense to use them, because likely that would be a very shorter path, probably. So in SSC mode 2, the 5G behavior is the following. You have an IP address that changes when the device leaves a network anchor's service area, and it will change to another IP address. And this is a break before make IP address change. So in this mode, MPTCP should use some break before make behavior similar to what exists now, except that this time it could occur even only on cellular. And similarly to the existing break before make behavior, the application should not request a specific network interface in this case, for example, when opening a socket for the same reason as in the current mode. And finally, MPTCP should maintain a valid backup IP address by using this same break before make behavior. Okay, in mode 3 now, the IP address changes when leaving a network anchor service area. And this is a make before break on the same or new network interface. Both cases can occur. And the lifetime of the old IP address is communicated by the network to the device using a routing advertisement. So in this mode, MPTCP should always create and use new subflows when a new IP address becomes available. And it should stop, to this application, to a particular application, yeah. It should stop using older subflows gracefully and should do that, in a way that help for performance and also helps recycling resources faster. So it should wait a little bit for the slow start to finish maybe, but then it should release the old IP address before it actually released automatically. And then MPTCP should not close subflows using the latest IP address, since this IP address is the only one that will remain after a transition period. And finally, it should maintain a valid backup IP address using the latest SSE Mode 3 IP address for that application. Okay, so now the other part of the draft, that's about dual connectivity in 5G. That's from a research project. And basically, the 5G behavior associated with dual connectivity that is the following. So DC relies basically on two paths over radio access, and individual QoS flows will use one path or another. And so typically, dual connectivity is not visible outside of the radio access technology layer. So the proposal made in this draft, the dual connectivity feature of 5G could leverage Mptcp to support a range of features, robustness, reliability, and bandwidth aggregation, without duplicating this in the 5G stack. To use Mptcp for dual connectivity, we identified roughly, for now, two requirements. There should be multiple DC radio links that should be exposed by 5G for use by Mptcp. And Mptcp should split or possibly duplicate traffic between subflows over different DC radio links. So, okay, that's the last slide on next steps. Of course, we are here to collect feedback on this draft. Is this valuable for Mptcp and for 5G communities? And if we want to move the draft forward, we can refine somewhat the SSC aspects, develop further the dual connectivity aspect, integrate feedback, and maybe, in the draft, in a section, identify clearly the requirements for Mptcp and if there are any for 5G as well. And of course, we are looking if anyone think of any additional 5G feature that could potentially impact Mptcp, so that we could gather that in one draft. So basically, you just wanted to add, this is for release 15, so I believe that the completion of the work in the specification that this year and the deployments could occur in 2020, I think. So that's it. Thank you.
Comments and questions?
Xavier, are you actually planning to do some experiment with this one?
No, there are two parts, right? On the service and session continuity, this is based on an analysis of the specs. Nothing else. On the other one, that's based on the research project from an ICT. So maybe maybe some of them are here and can maybe explain a bit more this part.
I think you may have half answered this already. I just wondered, have you presented this directly to anyone in the 5G community so far?
No, not so far.
Are you planning on?
That's a possibility. It depends also on how it's, what happens here, a type of discussion here. But we have people in our company who are going to 3G, and I think that's a clear possibility to try to make, especially we propose, we say that there could be some impact on Mptcp, but we also, for the second part, that would have some impact on 5G. So of course, in this case, we will need to present that in the 3PP.
Okay, sure. Thank you.
Cisco. So I'm trying to understand this proposal. So I understand address has different properties, right? Essentially, if you forget the 5G terminology, right, at the end of the day, there are addresses which are short-lived, there are addresses with mobility property, there are addresses with whatever, right? So somehow, if I understand correctly, you want this to be exposed to the Mptcp layer. Is that the objective?
Thank you. I'll try to clarify in this case, the goal of this. The 5G stack will behave in a certain way which is different from 4G or and so if we our point of view on this is that if we keep exactly the same behavior in Mptcp, the assumptions will be wrong, because really the way, I've tried to present it here, the way 5G handles mobility is different. And you see, like, you have these three modes. Before you had only one, right? And so before it was, I think, more similar to mode 1 now. So now it's kind of exploded. It's more distributed. So there isn't, it can be leveraged to get a better behavior, better performance from Mptcp.
As Father, I'll answer the question. It's, possibly, yes.
Okay. So I think a couple of things, right? Essentially, the way this one data point is in DMM. There is, for all of these modes, we are defining properties. In other words, as part of the ND procedures or as part of the array, extensions, the idea is to essentially include some additional information about the type of address. In other words, when a host gets an address, it know what is the type of address, right? Now, 3GPPs, all of these modes will map to the IETF specified coloring. Okay, if I call it as a coloring or whatever properties, that all of these three modes will have one-to-one mapping to the modes that we are defining. We'll be defining in DMM working group. So that is one aspect. So that addresses some part of your concern in the sense that addresses have different properties, whether mobility and non-mobility. That from when you obtain an address, that those property will come as part of in the address assignment procedures. Maybe DHCP-v6, maybe neighbor discovery or IQ to control protocol. That is one aspect. Now the second aspect, probably what is missing, is how do we expose that to the socket layer? That also in DMM working group, somebody has specified extensions. It's a working group document. It's already passed last call. There we expose that to the higher applications. At application layer, if you use a standard socket interface, with that, you know exactly what is the type of address. So now, if I add those two things, now I'm wondering, like, if an application is using Mptcp with those socket extensions, is there still a problem? Is what I'm thinking. So maybe I haven't read the draft. I just looked at the INA section. It doesn't say anything. No actions are required. Maybe you're specifying certain behavior. I do not know, but I strongly suggest look at the work in DMM working group. Maybe there's a gap. Maybe there's no gap. But I feel it's addressed to most part.
Hi, thanks for the information. Actually, the 3GPP sent a license statement for DMM working group for the prefix map coloring, right? So that's what you're talking about. So I looked into that draft and I looked into requirements and also the draft he's talking about. So this draft is all about how these requirements are mapped to MPTCP, if there anything residual need to be done in MPTCP to address SSC mode 3. That's what it's looking into. So it may be possible that nothing significant need to be added in MPTCP, but it's good to have the requirements put it in one place, because 3G people are tracking all the drafts related to 5G, and they'll watch and they'll come back to this if they want something need to be added.
Yeah, thanks for the clarification. I think I'm okay with this, but I'm trying to, at this point, the requirement is not clear to me. I understand, 5G has different things, but already there's work happening. I think if this on top of that is a new, if you can clearly articulate what that is, maybe if it is impacts MPTCP, it's fine. But otherwise, at this point, I don't see that impact. So, but again, I'm open for correction.
Thank you. I mean, I guess, I think we have to do some work with to check the DMM drafts. Thanks.
So Philip Erdley, just to follow up on that. So I haven't quite understood in terms of this DMM work that's been done so far. Would you be able to use somebody choose to be able to use multipath TCP to do this DMM mobility that's being done for 5G, or so are changes needed on your side to be able to use this, or can you use all of this multipath TCP stuff that Xavier's been working on anyway? Yeah,
so the way I see it, Philip, like if you are already exposing these 3 classes or the modes into the socket layer, now if there's an application sitting at the which is opening up sockets, already you have the visibility. Like anytime you bind to a particular IP address, you fetch get in for whatever, like the property of that address, class 1, mode 1, mode 2, mode 3, right? Now I ask the question back. Now that layer, now it's visible to the application. Now, are you going to define some additional logic saying that, if you see this, do this, or is it, informational spec what it is? No, but it's available. The information is available. My point is.
Okay, so what I get is that based on this DMM work, the MPTCP would be able to get in which mode a particular interface is attached to, right?
Yeah, absolutely.
Yeah. And so additionally, maybe it's done also, I don't know, but you see there is a sort of mapping, like if a new interface goes up, it's visible or it should be usable by some applications, but not others, because the application that goes up relates to one slice or one SSC mode that's covered. But you see that some applications will not be able to use that particular interface, maybe, and maybe able to use others. So there is a sort of mapping between interfaces and applications, which is known by the 5G stack, which normally the application doesn't need to know, because the stack will expose the interface that is visible by this application. But since MPTCP is between the application and the 5G stack, there may be something needed there for this type of mapping.
Yeah, fair point. I'm trying to understand at this point. It's not clear to me, but I'll think about it. I think the way I'm not 100% clear.
So it sounds like, sorry, Philip Erdling, sounds like we need to make sure kind of about this interface between the DMM work and the multipath TCP being used for mobility, and we should make sure that the two things are joined up.
We need to make sure we are on the same page. Absolutely.
Yeah.
Maybe
might not
we
be
can
at the moment.
talk quickly, and after by email maybe, so to point us to the right place. If there is nothing to do, that's fine. Our goal is to go as far as needed to see what was needed, and if there is no work is needed, then that's it.
Let's understand. That's
Thank you.
And Zambi, just one other question. So in terms of what you've talked about, I didn't see any changes required on multipath TCP. You've been talking about how to use it, which is great. Am I right that as yet you've not found that any changes that we need to make in this working group in order that the stuff is more useful for you?
At this point, I agree. There is. It's too early to say.
Okay.
It's possible, for example, what is possible that MPTCP may need to have access, for example, to a certain API obtained from the 5G stack to know which interface can be visible by which application. that I don't know if that already
Okay.
exists in some kind.
So I probably should be sitting over there, but I'd encourage you during this working group last call, if there's any changes that you think are needed to the protocol to help our stuff get used by 5G, please make the suggestions. Or if they're part of the API work, which it sounded like they might be more part of that, in these API discussions that are now milling about and will continue, please make the suggestions and work with the API authors.
Sure. Just a last word is I think that if most of what has been shown is in terms of MPTCP behavior, I think it's a type that would impact the scheduler or things like that. So I assume that will not impact MPTCP by itself, right?
Yeah.
So.
Can you remember who's next? Is it Quentin next on the agenda? Just trying to double check what we said. Yes, it's Quentin. Some experiment with the iOS stuff. Excellent. Here he comes.
So hi all, this is a quick informational presentation about some experiments I do with multipass TCP in iOS. So next slide. So Apple is probably the biggest deployment of multipass TCP that exists today. Initially it was made for Siri, and since iOS 11 it is available for all applications. So it's nice for a researcher point of view because you can try MPTCP with a lot of devices, and that's fun. So next slide. So the question is, how performant is multipass TCP about its design goals? So you have the bandwidth aggregation, but for the mobile case, it is not the case where you want to use multipass TCP, but rather for the network handover when you switch from, for example, Wi-Fi to cellular. And so how multipass TCP in iOS behave when you have different kind of traffic and under different scenario where you lose the Wi-Fi and you can continue the connection on the cellular. So next slide. So to assess this, I created an application which is called Multipass Tester. So you have two big kinds of experiment you can make. The first one is a mobile experiment when you can estimate how far you can reach your Wi-Fi by exchanging data over it. And so you have a bidirectional traffic and you see until when you can exchange data. And another multipass benchmarker when you try different kind of traffic and you compare with a single pass variant. And there is the ability to visualize the results, of course. And we compare multipass TCP with also quick and multipass quick. So yeah, and we see if it behaves equally well in those cases. So next slide. So since the deployment we made on 8 March, we had 205 runs, where only 22 were mobile runs. So most of the time, users do not want to move, but yeah, let's say like this. And 50 users, mostly from Europe, but we had a few from America, so that's nice. So next slide. So a concrete example of what we can observe with this is, for instance, here I show the mobile experiment where you try to estimate how far you can reach the Wi-Fi access point while sending data, and where you can see some results, live results of the experiment. So next slide. About the methodology, so you have the user that has his phone and it's connected to Wi-Fi, and then it moves to outside the Wi-Fi reachability. And during that process, we are running some streaming traffic. So in both upload and download, and we see how the multipass protocols behave like this. And we use the interactive mode. So it is the mode that was designed for Siri, and we want to see if for any kind of traffic like this, it is sufficient. And so we collect the application latency between when we send a data packet in streaming and the acknowledgement at applicative level. And the test stops when the system considers the Wi-Fi as lost. Either it considers Wi-Fi as lost because it is not reachable anymore for the system, or the BSS ID change. And so some results, next slide. So about what we collect as results so far is, here you have a cumulative distribution function over the mobile test where the Wi-Fi was actually lost. And so we show the maximum applicative delay experienced by the application here in the upload direction by comparing Mptcp and mpquick. So we see that in most cases, it seems that it works well, but we have a long tail distribution at the end where there are more interesting cases where it seems difficult to perform handover efficiently. And so next slide. In the load, we also observe the same behavior. And the next slide. And so, currently we only have 10 users, so it's not a lot. So the idea is to, of course, collect more data about it. And so we are looking for volunteers, and we push interesting results about those findings on multipassquick.org. We push one about address validation of Quick, but for multipass-TCP, we also have some interesting results. And so next slide. So if we want to give it a try, you can have the application here, and since it's still in development, feel free to provide feedback. And yeah, that's it.
Comments, questions, suggestions?
Okay, Yoshi from Floor. So yeah, thanks. This is very interesting experiment. Thanks so much. And so I tried to understand what's the difference between the scheduler in multipass quick and the multipass TCP.
So yeah, in that case, so far, so I have my own implementation of multipass quick, of course. And in both cases, at server side, we are using a classical lowest latency first.
Mm-hmm.
And at client side, it's also lowest latency first, but considering also the fact that you prefer the Wi-Fi over the cellular. So you have some network prioritization over the Wi-Fi until you consider the Wi-Fi as too bad and you switch on the cellular.
So naively, choosing lowest round trip time is not works very well. That's what you're trying to say?
So far, we are based on RTT mainly, but I know in the Linux implementation, for instance, you have also when a path is considered potentially failed when you experience a lot of losses, and so you avoid sending on that path until you see it works again.
Mm-hmm.
So I suppose there is something similar in iOS, and for multipass quick, it uses that so far. But of course, the scheduling, this is a work to improve, of course, the scheduling algorithms and also the path management and so on.
Probably it's very difficult to ask what's inside iOS multipass TCP scheduler. Okay.
Zhen Cao. So thanks for the work. It's very interesting. I'm trying to understand why the iOS Mptcp is better than mpquick in one of your figures, right?
Yeah.
For the Macs.
One of the stuff is that because I had a quick look at the trace. Sometimes my multipass quick implementations tries to send on the cellular while it should not. And so it increases the delays because sometimes you have out of order delivery, and also at some performance issue with multipass quick, but I'm fixing them. So it's an iterative process about fixing the scheduling issue with multipass quick.
But if the MP quick, sends the request at the time that it ought not to send that request, then you should not count that infinite number into account, because that's kind of fair, right?
Sorry?
Because if the quick doesn't go through the network, I mean, you are going to send the quick at a cellular link, but the cellular link doesn't work at that time.
Yeah.
But that data should not be taken into account. So my impression is that if you have a threshold to make the handover decision, anyway, at this at handover point, you should send the request. Then the maximum delay should be actually the same for the two approach.
It should.
Okay.
It should, and so I will also investigate.
Yeah, probably
why
we can see the formula if we have more data.
Yeah.
But thank you for work.
So.
You don't have a comment.
Thanks. So next up is Anthony, who's doing it remotely, isn't he? So I can see you're on Meet Echo, Anthony. I think you have to request.
Request.
Welcome, we can hear you.
Okay. Okay. So we start with the. Is the slides on yet? Hello, others.
The slides are being displayed. Yeah.
Oh, okay, I couldn't see the slide. Oh. This talk is on the one-way latency measurement and on the need of the slide. And on page 2, first of all, we start about the justification on what the problem is. Basically, in cellular network, the data rate is not symmetric in the uplink and download direction. For example, when we look at the FH Global 4G download rate, it's in the 16 to 7 megabit per second. But what they didn't tell you is that the upload speed is much slower. For example, in the LTE, one of the example of that you really have to look at the small pin and the difference between the upload and download. In this case, a typical provider is saying that the download is 5 to 12 megabit, but the upload is only 2 to 5 megabit per second. So we are used to measure the round trip time, and for the access part, the upload and the downloads are very different. And then in the next slide, number 3, it's different, not just in the client side, it can also be different in the server side. So we are struggling with rate, and so basically, what we are proposing is that the round trip time measurement is not sufficient. And in the next slide, number 4, page number 4, is going through the one of the reasons for the asymmetry. If we take the 3GPP network, it first of all, it has to look for the control channel to, when you do an uplink, you have to look for the uplink on the left and the downlink on the right hand side. You have to look for the channel to allow you to go downlink and uplink. And depending on whether the transmission time interval is 10 milliseconds or 1 millisecond, you have to wait 5 or half millisecond. And after that, that will allow the user equipment to send the scheduling request to schedule a channel for the UE to send the data. And then the UE will process the request, and then and then the INOP the base station decodes the request and generate the scheduling grant, and then send a scheduling grant to the user equipment, and the user equipment will have to process it and then finally send the data. So on the average, it's about 17 or 12.5 millisecond, depending on the time slot interval. On the downlink is different. It's only processing the incoming data from the for the base station, and it aligns with the times the transmission time interval, and then it would transmit the download data, and then the UE decodes it. So it's about 7.5 milliseconds. These are the numbers in the 4G. In the 5G, the number would be different. In the next slide, and how about the access? Besides the access, that was only for the previous slide was only talking about the uplink and downlink in the wireless access part. And when you get to the network with the routers, there are going to be queues. When there's a queue on one direction, it doesn't mean the other direction also have a long queue. The internet doesn't need to be congested in both directions. But if you have a long queue in one side, the round trip time is going to be increased. So that is again not the good measure. In the next slide, page 6. What the user need to do is facing a number of asymmetry. The asymmetry is not just for the wireless. If we look at the typical internet service provider, they typically give you a higher download speed versus the upload speed. In an example is that the FCC in the United States defined the definition of broadband. If you had prior to 2015, if the minimum speed for the downlink is 4 megabit per second and the uplink is 1 megabit per second, and it is considered broadband. And it is based on a number of measurements that is made so that they made such a definition. And in 2015, we defined the definition of broadband. So basically, a service provider, if providing a broadband service, it has to provide the minimum data rate of 25 megabit per second download and 3 megabit per second upload. That's just the minimum. But if it is mobile, it is a little different. And the reference is down there. So basically, besides the wireless, we also have internet service provider providing asymmetric data rate for the user. So in page 7 is that, so what it boils down to as far as mobile TCP is concerned, we are picking different paths. And one of the criteria is to pick the path with the shorter delay. And if we just look at the round trip time, it doesn't tell us the whole story. And the two paths could be two wireless on the left-hand side, and then in the middle, it could be a wireless in one connection, and another connection could be a fixed connection. And in the third case, on the right-hand side, it can be such as a business. It could be dual home to two service to ISP, and it has a choice of picking which one to use to get the higher speed. And then on page, so if it is not, so if the round trip time is not enough, we would be looking at the one-way delay. And if we measure the one-way delay, in the past we had to synchronize both clocks, and we don't. First of all, we don't have enough information to measure both. We basically check what time you send the packet and what time it comes back, and then measure the round trip time. If we had to measure the round trip delay or the one-way delay, we would need to know the time the receiver received the packet. So one option is to synchronize the clock and then the acknowledgement or SACK, which could be a delayed one. So the round trip time will be even more inaccurate. And in the acknowledgement, it would have to include the time that the packet was received, so that the receiver can calculate it and then take a difference. So in one path, like path I on the left-hand side and the right-hand side, a different path J, and it measures the one-way delay and then calculate the difference. And then in the next slide, page 9, is that if all we care is basically the difference. We only want to look at the difference. And if you look at the difference, whether you synchronize the clock or not synchronize the clock, it really doesn't matter because it cancels out. So on the right-hand side bottom, you are getting exactly the same result, whether you synchronize the clock or not synchronize the clock, although the measurements are not accurate because of the synchronization. But because you're between the same sender and the same receiver, but two different parts, the clock synchronization, the clock error cancels out, so you're getting the same result. So there is value. So the proposal is that there's a value to measure the one-way delay, and that would require an addition to the standard. So in the next slide is that first of all you have to negotiate whether you are using this additional option or a subtype or whatever you're going to use. It could be a subtype of the multipath type message that you're adding. And then on page 11 is talking about there are many different approaches to measure the one-way delay or latency, and we would like to hear from your feedback whether this is one of the approach. What was outlined before in page 8 and 9 was that the client just remembers the time you send out the packet, and then receiver only had to send the time the packet was received. There's only one information that the receiver changed it, and when the client received the time it received the packet, it will calculate the difference and then take the and then compare between the different paths so that it will pick the best path to send the packet. And an alternative in the next one is that the client doesn't need to remember the time sent. It will just use a timestamp to send it, and then when the receiver gets it, it will echo back the time sent, but it will still have to add the time received. And so the difference is just the client doesn't need to remember the time, but it does have to add a timestamp in the packet that it's sending compared with the previous one. And then again, it will just compare the different path and then pick the better route. And the another alternative in the bottom is that the server the timestamp and server will calculate the difference and then send the one-way latency back to the client. So the client doesn't need to do any computation. They only need to compare the one-way delay. So there are pros and cons depending on what you need. And then in the next slide, page 12, is that how speed that is more straightforward, and it probably doesn't need an additional changes in the standard. Basically, if the server side send a packet in the download direction with a timestamp, then the client knows what time it received it. Then it will just calculate the one-way latency. Now, this one-way latency do have the time error because the two clocks between the kind of servers can be different. It may or may not be different. And
Anthony, I'm sorry to interrupt, but you're breaking up a lot at the moment.
Is there a question? Hello?
No, I think the connection's gone a bit down.
Oh.
So I think Well, I stopped being able to understand it. We were getting about every other word. I think you were just about at the end, weren't you? It's gone. I think what we should do is move on to the next presentation, which is linked, shouldn't we? And then come back.
Okay.
Sorry, I think it's just it got to the stage it was very difficult to follow. So we'll try coming back, because I know you're linked to the next talk from Ying. So Jing, do you want to come up and do yours? Because I know you're kind of building on what Anthony's just been talking about. And then maybe we can have questions for the two together.
Hi, everyone. Okay. So my name is Jin Zuo, and I'm from Huawei. So today I'm going to talk about a path-aware networking scheduling scheme for Mptcp. So next. Nowadays, we have lots of applications which are latency sensitive. They require the data delivered as soon as possible. Currently, the RTT is commonly used as a condition for data scheduling amongst multiple paths. However, as just described by Anthony in his slides, the delays of the forward path and the reverse path may be different, especially in the wireless environment, and also in the scenario when the congestions may not happen the same, so which will cause the different queue delays. So it's better to consider the one-way latency for the data scheduling. Next. Okay. We have several examples and to show why the one-way latency should be considered for the data scheduling. This picture shows the scheduling based on the RTT, and there are three paths between the client and the server. And we can see that based on the RTT, so the path 2 will be selected for the data transmission. Next. Okay. In this picture, if we consider one-way latency as a condition for the data scheduling, then we can see that if the client want to transmit the data to the server, then we can see that the path 1 have the lowest one-way latency compared to the other two paths. So the data will be scheduled in the path 1 based on the one-way latency. Okay, next. This picture, if we consider in the interactive latency, if the client transmit data to the server, okay, the data will be scheduled in the path 1, while the ACK will be scheduled in the path 3. So by sum up the latency of the path 1 and path 3, so we can see that the return latency will be 12 milliseconds compared to the RTT in path 2, which is 16 milliseconds. Next. Okay, so we propose a new path-aware scheduling scheme. And the basic design principles is that we always send the data in the path with the lowest one-way latency. And because the one-way latency may change, so we periodically update the one-way latencies of all paths and schedule the data again. Next. We will explain the scheduling scheme in 3 steps in details. So first, let's see the initialization stage. So here, during the initialization, so we have no path characteristics for both of the paths. So, and also Mptcp sets up the connection of the primary paths first, afterwards, and then sets up the connection of the other path one by one. So at that time, the redundant transmission can be used to transmit data on all the paths and to obtain the effective one-way latencies of all the paths. We can transmit data redundantly for a period of time, for example, 1 second. Next. And after we obtain the one-way latency, so we schedule the packet according to the one-way latency. And we can see that before, if we only consider one-way latency of one path, you may think there is a time synchronization problem there. But here, because we want to select the path with the lowest one-way latency, so by comparing the one-way latencies of the two paths, the time synchronization issue won't exist anymore because the difference of the absolute time clock will not exist, will be subtracted. So here, we compare the path 1 and path 2 of the one-way latency. So if path 1 has a lower one-way latency, so we select path 1 to transmit the data. Next. So as we know, the network environment will change because in the wireless environment, we may have packet loss, random packet loss, and also we have lots of flows coexist in the network. Some flows come in and some flows go out. So we better to obtain the one-way latencies and to see whether they change or not. So here we use a periodical redundant transmission to get the updated one-way latencies. Here we define every 10 seconds, we go back to the redundant transmission and to see whether the one-way latencies change or not. Here, while we use the redundant transmission to do the measurement of one-way latency, the reason is that because the redundant transmission transmit the data in all the paths in the same time. So you can get the one-way latencies of all the paths at the same time. At the same time, you do not need to measure them one by one. And the other reason is the redundant transmission, because they transmit the data, so they won't introduce extra packets. And the third reason is that the redundant transmission can guarantee the lowest delivery time, no matter which path it goes through. Next. Okay, there is a case you have to immediately activate the redundant transmission here, because if the path 1 is selected for the data transmission, and then you can know whether the one-way latency of that path changes or not. If you found that the one-way latencies of that selected path is not the lowest anymore, so at this time, it's better to activate the one-way latencies immediately. The redundant transmission immediately. Okay, next. So here we consider the implementations, because you need to know the one-way latency. So we need to define a multipath TCP option, which is called multipath one-way latency option. And this option is used to carry the timestamp of the data receiving at the receiver. Here, the can equals 30, which means that this is multipath TCP option. And we define the subtype as the 0x8, since the 0x0 to 0x7 have been defined. Okay, next. So for the one-way latency calculation, so first negotiation is needed to ensure both the sender and the receiver support multipath one-way latency. And here we use the sender to calculate one-way latency. The reason is that because the sender needs to compare which path has the lower one-way latency. So we just let the one-way latency, the sender to do the calculation. And the other reason is that because if you use the sender to calculate the one-way latency, and which means that the data packet does not need to carry the timestamp of the sending time. Okay, next. So that's it. Any questions and comments?
Any comments or questions for either on this one or on the previous one from Anthony? Jing, what's the status? Are you have you built this? Have you coded it? Is it?
We have a team and to do something. Yeah.
You're intending. You will do. but not yet.
Part of them already done.
Okay.
Okay, so this is Yoshi from Floor. So if the path is completely disjoint, yeah, it makes sense to send the redundant mode. It makes sense to measure one-way delay. But if the path is jointed, and then if you use redundant mode, then all data is on the same path. And then in this case, still, does this works for one-way delay measurement? Does it affect? Or have you ever considered this kind of scenario?
I'm not sure whether I got your point or not, but if one path join in, so which means you have no information about the path. But
if you use redundant mode, and then each subflow compete each other to eat bandwidth each other, and doesn't it affect the bandwidth or round trip measurement result or not?
Because the redundant measurement is just run for a period of time, so it's okay.
Mia Kudovan, why can you just not use the TCP timestamp option that you have on each path?
Because the TCP timestamp option is already has its own meaning, and for the data packet, it carries the timestamp as a sending time. But in ACK, so it carries two timestamps. One is for the sending time of the data, and the other one is for copy the sending time of the data, and one is the sending time of the ACK. Yeah. So we do not want to change the meaning of the timestamp of the option in the TCP option. But it's okay if you think the timestamp option can be used, so we can use that.
Yeah, maybe I'm missing something. So what would you need to change?
We use ACK packet and to return back the receiving time of the data and to the sender.
So instead of putting the timestamp in when you send out the ACK, you want the timestamp when you receive the data?
Yes, because there is a time difference between the time of data receiving and the time of sending the ACK.
Okay, there is a data difference, but it's a small one, right?
If you use this ACK or delay ACK, it won't be.
Okay, yeah, we had this problem. Okay, but in any case, I don't think that measuring one-way delay is a specific function you need for. I see a use case for MPTCP, but it's a functionality that should not be provided in an MPTCP sub option. So if you want a different timestamping mechanism in TCP, it should be a TCP option.
Okay.
Mark Handley. I've been trying to understand what you actually do in the redundant phase. So do you transmit each packet simultaneously on the multiple different paths, or do you just let each of those do its own congestion control thing during that simultaneous transmission?
It transmits simultaneously, but it depends on the interface, so whether it can be sent out or not.
So if you've got a path that simply can't cope with that data rate and you go into redundant transmission, which of the two paths then does the congestion control if you're trying to transmit packets at the same time on both interfaces?
So currently we don't consider about the congestion problems.
Because if you either each interface needs to separately do congestion control, or if you try to transmit packets simultaneously, you've either got to do some kind of joint congestion control across both interfaces or have one of them drive the other one. And I just don't quite understand how you propose it to work.
I think it would be better to consider the uncoupled congestion. Yeah, they just transmit separately and do not consider the congestion window.
Okay,
yeah.
And so if you switch into your redundant mode for, say, a second, but the second path you've just added is going, say, 10 times slower, it will then take 10 seconds to transfer the data that the first path sends in 1 second. Do you give up at some point and say that's just going to be too slow, or what do you do?
Yeah, we can set a threshold into that, but the problem is that you don't know what the exact value of that threshold. Yeah, so that's why we didn't consider currently.
Okay, thanks.
Thanks. So we've got one more presentation, which is from Vlad, which is an update on the SOX work, which is being done in the Int working group, but kind of relates to multiple TCP. So this is kind of for information in the last about 4 minutes we have left.
Right, hi. I'm going to give you a quick update on SOX version 6. So next slide, please. So as you may probably know, SOX 6, in SOX 6, we've been busy trimming down the RTT overhead. Right now, if you're using zero RTT authentication or no authentication at all, the overhead is 0. In terms of protecting against malicious third parties, we've decided to take a step back, and rather than do encryption within the protocol, we just run it over TLS. Now SOX version 6 also mitigates early data replay attacks, so it's also safe to use TLS early data. And new in the latest version of the draft, we've added a SecSocOp-like mechanism, and we've used it to implement a couple of Mptcp use cases. So next slide, please. So first up, in this latest version of the draft, we've also specified how to perform plain text password authentication. This is actually viable now that SOX also runs over TLS, and we expect it to be the de facto standard. So you simply take the initial message of the exchange from RFC 1929, and you place it in a SOX request as an authentication data option. There's a small caveat though. If the username and password are exceptionally long, they won't fit, and you still have to do the regular authentication, which takes 1 RTT. Next slide, please. So these are the socket options that I've been talking about. Clients can place them inside SOX requests, and proxies can place them inside operation replies. Clients can use them to request certain behavior from the proxy on either of the legs, either the client proxy leg or the proxy server leg. And these options were heavily inspired by setSocOpt and getSocOpt. However, they are not a remote procedure call for setSocOpt and getSocOpt, and their individual semantics and individual options and their semantics have to be standardized separately. There was some discussion on the mailing list, and they will be renamed because sockets are actually an OS concept, and TCP connections don't necessarily require sockets in order to implement them. Now, the fields I want to draw your attention to are leg. So a socket option can either apply to the client proxy leg or the proxy server leg, or both legs at the same time. And the next 3 fields, level, option code, and data, were basically ripped off from the setSocOpt and getSocOpt API. So you've got socket levels for layer 3 and layer 4 protocols. We've also got the socket layer for a generic socket layer. And the option, and then you've got the option code, and the data depends on each individual option. So next slide, please. The simplest use case we found for these options is TFO. So there previously was a field in the request which the client could use to request the proxy to use TFO in its connection attempt. Now that field has been removed and it's been replaced by an option. The absence of this option means that the proxy must not use TFO. Next slide, please. Next up, we've implemented an option which can be used for proxy bypass. You're probably familiar with this use case. So let's say a mobile phone has both a Wi-Fi and a 4G interface, and it wants to take advantage of both. However, servers typically don't deploy MPTCP. So the mobile phone has to go through a proxy first. Now, if the server happens to support MPTCP, the proxy can let us know by including an MPTCP option in its operation replies. Next slide, please. So in further connection attempts, the client can just contact the server directly and forgo the use of the proxy. Next slide, please. We've also implemented an option which allows the client to specify its preferred MPTCP scheduler. And we currently support all of the schedulers that are part of the Linux MPTCP implementation. So a client can place one such option in its request to ask the proxy to use a certain scheduler on one leg or both legs, and a proxy can include one such option in the operation reply to tell the client, to inform the client as to what scheduler it's using on one or both of the legs. We found a use case for this. So if a particular application requires extremely low latency, it can ask the proxy to use the redundant scheduler and have the data be duplicated across all available paths. And that's about it for me. Any questions?
Where are the blue sheets?
Questions?
Is there a blue sheet?
Yeah. Actually, Brad, I have one question. Brad, can I ask one question?
Of course.
About the bypass mode. So also when the client identify the server support multipass TCP, that means application cache the information and they utilize for next.
Yes.
So it doesn't like socket sock cache the information and automatically reconnect. It's not like the application has a responsibility to use the information.
Yes, that's right. So in terms of implementation, the application is probably a proxifier. Then you can add IP tables rules that bypass that don't proxify connections heading out to that particular server.
Okay, got it. Thank you.
All right.
I think we're out of time.
All right, so thank you.
Thank you very much, Vlad, for the
Thank you for
update.
having me.
Thank you, everybody, for the good presentations and discussion today. And you will see some last call soon, which please go in, make comments. A comment, I've read it and I don't have any comments, is a good comment, and that's useful on all of it or on part of the document. Everything is valuable, all feedback. Thank you very much. See you next time. Bye-bye.